Optimization. In optimization problems, the goal is to maximize or minimize something, like volume, area, or cost. For each problem, you will need an equation for what you are trying to maximize or minimize, and then a second equation called the constraint equation, because there are always restrictions in life. We only have so much material. So this is used to plug into the first equation so that there's only one variable. Then you will need to differentiate the equation, find the critical values, and answer the question. Alright, here we go. You have been asked to design a 1,000 centimeter cubed can shaped like a right circular cylinder. What dimensions will use the least material? So what I'm going to go ahead and do is just go ahead and draw a right circular can, a right circular cylinder. And we're talking about its volume. We're told that the design needs to be 1,000 centimeters cubed. We're talking about the dimensions. So I'm going to label the dimensions as R and H generically, the radius and the height. And what we're trying to do is minimize surface area. So the surface area, I'm going to go ahead and call S for surface area. I have to write an equation that represents the surface area of this right circular cylinder. So the top and the bottom are both circles, so the area of a circle is pi r squared, but there's a top and a bottom, so 2 pi r squared, plus the surface area is the entire can all the way around. So if I think about that for a second, if I cut the can down the side and unraveled it, it would look like a rectangle. So the side of the rectangle here would be that height h, and then all the way around, which is this base here of the rectangle, would be the circumference of a circle. And the circumference of a circle is 2 pi r. So that means that the surface area is 2 pi rh of the area around the side of the can. So plus 2 pi rh. So this is the equation that we are trying to minimize. Now currently it has two variables in it. I have r and I have h. So what I want to do now is think about my constraint equation. I have a restriction. The design has to be only 1,000 centimeters cubed. That's a volume. So I have my constraint equation. So we're going to start out with the generic volume formula, which is pi r squared h, but we know the volume is 1,000. So 1,000 pi r squared equals pi r squared h. So what I'm going to go ahead and do is solve this constraint equation for h. So I'm going to divide by pi r squared on both sides. So 1,000 divided by pi r squared is equal to h. And then I'm going to go ahead and take that quantity and substitute it in over into the equation I'm trying to minimize so that it's all in terms of the same variable. So now I want to go ahead and simplify this, so I end up with 2 pi r squared plus I'll have 2,000. The pi's will cancel and an r will cancel, so 2,000 over r. Now that's all in the same variable. I want to be able to take its derivative, so before I do that, I'm going to do one more thing. I'm going to write 2 pi r squared plus 2,000 r to the negative 1. So I can apply the power rule to take the derivative. So my derivative, s prime of r, I'm taking the derivative with respect to r, is 4 pi r minus 2,000 r to the negative 2. And I'm going to need to rewrite this as a rational expression. So I have 4 pi r minus 2,000 over r squared. And I want that common denominator of r squared, so I'll multiply the top and bottom by r squared, and I'll end up with 4 pi r cubed minus 2,000 over r squared. And I want to know, where is that equal to 0 or undefined? So it's equal to 0 when the numerator 4 pi r cubed minus 2000 is equal to 0, and undefined where r squared, the denominator, is equal to 0. So here we have pi r cubed would equal 500. Divide by pi, I get r cubed equals 500 divided by pi, or r is the cube root of 500 over pi. And over here I get r equals 0. However, it doesn't make sense for the radius to equal 0 if we're going to have any volume on our can. So r equals 0, this quantity doesn't make any sense. So this is not a critical value. So my only critical value is this cube root of 500 over pi. Now, since this is a critical value, we do want to justify that this is in fact a minimum. So we're going to go ahead and apply the second derivative test here. So I have s double prime of r, so I'm going ahead, this is s prime, I'm taking the derivative. I'll get 4 pi and then plus 4,000 r to the negative 3. Or 4 pi plus 4,000 over r cubed. But the only thing is the r values are the radius of my cylinder. So r has to be greater than 0. So what that means is that for any value of r that I substitute in here, since this value is positive, the second derivative is always positive. So if the second derivative is always positive, so I know that s double prime of r is greater than 0 for all r greater than 0. So s must be a concave up function, and we can apply the second derivative test, so we know that any critical value must be a local minimum. So by the second derivative test, so I'm going to say by the SDT, our function s of the cube root of 500 over pi is a minimum. So we've justified it, we've showed that this is a minimum, but now we have to make sure and answer the question. The question asked us what dimensions will use the least material. So the dimensions are the radius and the height. Well, we found the radius, so the dimensions, the radius would be the cube root of that 500 over pi, and the units there are centimeters. So we also need h. We also need the height. Well, here's what we know about the height. The height from our constraint equation was 1,000 over pi r squared. Well, we don't want to leave our answer with r in it. We can now replace r with our value, the cube root of 500 over pi. So our other dimension is 1,000 over pi times the cube root of 500 over pi squared. So these are the dimensions that use the least material. So least material means minimize that surface area. And we want to make sure and include centimeters. In this next example, we're told a poster is to have an area of 180 inches squared. So I'm just going to pause right there. That's our constraint, that's our restriction. This area has to be 180 inches squared. With 1-inch margins at the bottom and sides and a 2-inch margin at the top. What dimensions will give the largest printed area? So let's go ahead and draw a picture. So here we have a rectangular poster, and I went ahead and called the entire base of the poster X and the entire height of the poster Y. And then I also went ahead and labeled these 1-inch margins on the sides and on the bottom, and this is a 2-inch margin on the top. So I'm actually going to start this one by writing out the constraint equation first. So the constraint equation on this one is going to be that the area, which is x times y, is 180 inches. So 180 is equal to x times y. And now let's go ahead and talk about what exactly it is we're trying to maximize or minimize. So what dimensions will give the largest printed area? So we are trying to maximize something, largest, the area of this inside region here. Alright, so maximize the printed area. I'm going to call this function A, and I need to go ahead and find the base and the height to find the area. So the base of this inside shaded region here, well, if the whole entire base is x, and I'm going ahead and taking away 1 inch from the left side and 1 inch from the right side, this inside part would be x minus 2. And then if I wanted the height, so the entire side is y, but I'm taking 2 off the top and 1 off the bottom. So this inside portion's height is going to be y minus 3. So the printed area I'm trying to maximize has dimensions base x minus 2 times height y minus 3. So notice it's a function of two variables, x and y, and that's where our constraint equation comes in. So I'm going to solve the constraint equation for the variable y. So I'm going to divide both sides by x to get y equals 180 over x, and then I'm going to substitute that in over here to the y variable. So now notice that a is a function of just x. I have x minus 2, 180 over x minus 3, and I want to take the derivative, but first I'm going to go ahead and distribute this out to make it easier to take the derivative of. So I'm going to have 180, the x's will cancel, minus 3x, minus 360 x to the negative 1, because I'm going to have inside here this 360 over x, so I'm writing it as x to the negative 1 plus 6. So now when I take the derivative, I will have a prime of x is equal to negative 3 plus 360 x to the negative 2. So now we simplify that to negative 3 plus 360 over x squared. So I would make the denominator here x squared, the numerator x squared. So we are going to set negative 3x squared plus 360 over x squared equal to 0, or undefined, to find my critical values. So to set equal to 0, I'll set the numerator equal to 0. And I end up getting x squared would equal 120, or x equals plus or minus radical 120, or x equals plus or minus, let's see, 2 radical 30. And we know that it doesn't make sense to have a negative x value because x was the side length of the base of the poster. So we only have x equals positive 2 radical 30 as a critical value. And to determine where the derivative is undefined, we set x squared equal to 0. So we get x equals 0, but that doesn't make sense. We can't have the base of a frame equal 0 and still manage to have any area involved. So my only critical value is 2 radical 30. We want to go ahead and show that at this critical value we have a maximum, since we're trying to find the largest printed area. So to show that we have a maximum, we're going to go ahead and use the first derivative test. We're going to create our number line, and our number line is going to start at 0 only because this is for x values, and we already said x has to be positive. So our number line will be from 0 to infinity. Our critical value is 2 radical 30. So we can pick our test point of, let's say, 1, and then a whole number bigger than 2 radical 30 is going to be 13. So if we substitute these test points into a prime, that will tell us about a. So if I substitute in 1 into my derivative function here, I'm going to go ahead and get out a positive number. So the bottom is always positive. If I plug in 1 into x squared here, overall the numerator will be positive. So a is increasing on that first interval. If I substitute in 13 into this x, I'm going to end up with a value that's negative and bigger than 360 in magnitude, so that means I'm going to end up with a negative, so I am decreasing. So I can see that I'm going to have increasing to decreasing. By the first derivative test, I would have a local maximum, but since this is the entire function here, I can see that this is really going to be my absolute maximum. So I have a max occurring at the x value, so at x equals 2 radical 30. But now we have to make sure and answer the problem. The problem said, what are the dimensions that will give the largest area? So the dimensions that will give the largest area are x equals that 2 radical 30 inches, and then remember from the constraint equation, y was 180 over x, so that's 180 over 2 radical 30, or 90 over radical 30 inches. So the other way we could potentially see the answer is dimensions are given as 2 radical 30 inches by 90 over radical 30 inches. In this next example, we're going to find the area of the largest trapezoid that can be inscribed in a circle of radius 1 and whose base is a diameter of the circle. So we are trying to maximize, so we have largest trapezoid, maximize the area of the trapezoid, but our constraint, our restriction, is that the trapezoid is inscribed, it lives inside of a circle of radius 1, and the base of the trapezoid is a diameter of the circle. So let's go ahead and draw what's happening. So as a reminder, a trapezoid has a base 1, a base 2, and a height. So I've drawn a trapezoid inside of a circle of radius 1. The circle is on the xy plane, so we can clearly see that the radius is 1, with the base along the diameter of the circle. So remember that we are trying to maximize the area. So the formula for the area of a trapezoid is given by A equals 1/2 height times base 1 plus base 2. What we want to do is we want to go ahead and make a connection to this point xy that's on the circle and also one of the vertices of the trapezoid. So over here in the area formula, we're going to go ahead and recognize that h, the height of this trapezoid, would be given by the amount y, the y coordinate of the point. That's how much I go up. So height is y. So I have so far that area is 1/2 y. And then base 1, so the base of this top part here, remember that this distance would have to be x. So this is x and this is x. So the whole distance across here for my base 1 is 2x. So I have 2x plus my base 2 all the way across here. If the radius is 1 unit in each direction, this entire base is 2. So base 2 is 2. So I now have my area formula in terms of x and y. I need it in terms of just one of those variables, so that's why we need to come over and find a constraint equation. The constraint equation is the equation of the circle. So the equation of a circle centered at the origin with a radius of 1 is x squared plus y squared is equal to 1. Now I'm going to solve for one of the variables. I'll solve for y. So y squared equals 1 minus x squared. So y equals plus or minus the square root of 1 minus x squared. And I can't take the square root of each piece. So here I have two different equations that came out, two different functions, positive radical 1 minus x squared and negative radical 1 minus x squared. So the positive part is the top of the circle. So y equals the square root of 1 minus x squared is the top of the circle, and the negative in front would be the bottom of the circle because it would be a reflection. So since I've constructed my trapezoid on the top of the circle, I'm going to choose this equation to substitute in to this y over here. So here we have our a as a function of just the variable x, so we can consider this a of x now. And I'm going to clean it up a little bit. This 1/2, if I distribute it into this binomial, would cancel out both of these 2's. So a is now the square root of 1 minus x squared and then times x plus 1. So this is my a of x, and I want to find a prime of x, which is going to require both a product rule and a chain rule. So a prime of x is the first function, 1 minus x squared, times the derivative of the second, so that's just 1, plus the second function, x plus 1, times the derivative of the first function is where my chain rule is. So I have 1/2, 1 minus x squared to the negative 1/2, times the derivative of the inside, minus 2x. So now it's a matter of simplifying this derivative so that we can find critical values. So let's go ahead and simplify this. We get the square root of 1 minus x squared for the first term, plus, let's see, the 1/2 and the 2 are going to cancel. So I have a negative x and an x plus 1 in the numerator. So I have negative x, x plus 1. And in the denominator, I have the 1 minus x squared to the positive 1/2 when I bring it to the bottom. So I'm going to rewrite that as the square root of 1 minus x squared. And now I want these to have common denominators, so I'm going to multiply the denominator over here by radical 1 minus x squared, and that's the same as the numerator here, so I'm just going to write it as that numerator squared. And let's see, that's going to give us 1 minus x squared minus x squared minus x, so I'm distributing this x here, all over radical 1 minus x squared. So I have 1 minus x minus 2x squared in the numerator, all over the square root of 1 minus x squared. And I want to know, where is this equal to 0 or undefined? So that means I'm going to need to set the numerator equal to 0 and figure out potentially where the denominator equals 0. So I have 1 minus x minus 2x squared is equal to 0, and this factors to 1 minus 2x and 1 plus x. So it gives me x equals positive 1/2 and x equals negative 1. And then we'll set the denominator, radical 1 minus x squared, equal to 0. So that's just 1 minus x squared equals 0. And that gives me just x equals both positive 1 and negative 1. But negative 1 and positive 1 both don't make sense. They both don't work. So if I go back just for a second to the picture, if I think about letting x equal either 1 or negative 1, I'm not actually going to have a trapezoid. So x was this distance here. So if I let x equal 1 or negative 1, I'm going to have just a flat line on the x-axis. I won't have a trapezoid. So now, let's go ahead and go back. The only critical value that I have is positive 1/2. So all of these are not critical values. We just have positive 1/2. And now we'll go ahead and justify that 1/2 is going to be a maximum value on this particular function. So let's go ahead and draw ourselves a number line. And that number line is only going to extend from 0 to 1, because those are really the only potential values that we could have for x. So, and in fact, I can't actually even have 0 and I can't have 1 because they're would be no trapezoid at that point if we let x equal 0 or 1. So our critical value is 1/2. If we pick test points like 1/4 and 3/4 to substitute into a prime to find out about a, so let's see, this is the most simplified version of a prime, or maybe even with the factored version in the numerator. But if we substitute in 1/4, we end up with a positive, meaning a is increasing, and substituting in 3/4 gives us a negative, meaning that a is decreasing. So we do in fact have a maximum at x equals 1/2. And now we need to make sure and answer the question. So the question was to find the area of that largest trapezoid. So we know that the area is going to happen or have a maximum at the x value 1/2. So let's go back and recall that the area function that we got was 1 minus x squared in the most simplified version times x plus 1. This is our area function for every x. So if the max happens at 1/2, then we're simply going to substitute 1/2 into every x. So 1 minus 1/2 squared, and then 1/2 plus 1, which is the square root of 3/4 here, times 3/2. So we end up getting 3 radical 3 over 4. And we weren't given any specific units here, but since this is an area, we'll go ahead and write units squared.